So let's talk about the roots of a polynomial. The roots or the zeros of the polynomial is something that you already know. And for quadratic equations, you can compute these. So quadratic equation, you have the formula that if p of x is equal to a times x squared plus bx plus c, then we know the roots or the zeros are given by x equal to minus b plus or minus the square root of the determinant divided by 2 times a, where d is b squared minus 4 times ac. So in general, we're going to define the roots and the polynomials as the complex values. So let's call them z, such that if you evaluate the polynomial at this value, you get 0. So for example, if our polynomial is equal to x squared plus 1, then we know that if we evaluate p on I, the imaginary constant, we get I squared plus 1, that's equal to 0. But also we have p evaluated at minus I, that's minus I squared plus 1, that's also 0. So here, plus and minus I are the roots. And now the question is, are these all of the roots? And this is a very important question that kept people busy over many centuries, and will state the theorems that we know about this. And in this case, the answer is going to be it's a quadratic polynomial. You have 2 roots, so yes, it's all of the roots. There's also a link with factors of a polynomial that I want to point out. So if alpha is a root or a 0, then x minus alpha is a factor. And why is that so? Well, if alpha is a root, that means that p of alpha is equal to 0. And we've already established that if p of alpha is equal to 0, then p of x has to be of the form x minus alpha times some other polynomial q of x. So x minus alpha is a factor. So let's put these definitions and the remainder theorem together for a couple of examples. So for the first example, let's try to find a polynomial of degree 4 with roots plus and minus I and plus and minus 2, so 4 values in total, and such that p of the value 3 is equal to 25. So we know the roots of the polynomial, which means that we know what factors to extract. We have a factor x minus minus I, x minus I, x minus 2, and x minus minus 2. So I write it out a bit in full, but I hope you see minus minus will become plus and so on. If you multiply this out, you have an x here, an x here, here, and here. So you will get, if you multiply these things together, a polynomial of degree 4. So we already have half of the answer here. And now we can multiply this polynomial by an arbitrary constant a without changing the roots or the factors. So now what do we know? Well, we also want p of the value x is 3 to be equal to 25. So let's see what p of 3 is. Well, it's a times 3 plus I, 3 minus I, 3 minus 2, 3 plus 2. So if you work that out, you get, for the first, if you multiply the first two terms together, you get 9 minus I squared. And then the next term here, that's 1 times 1, and then times 5. I squared is, of course, minus 1, so you get 9 minus 1, or 10. And if you multiply everything out, you get 50 times a, and that has to be equal to 25 from our condition here, is equal to 25. And so from that we see that our a constant is 1/2, and our polynomial becomes 1/2 x plus I, x minus I, x plus 2, x minus 2. And you can check that all the conditions hold. This is a degree 4 polynomial because you have 4 factors with x, and if you multiply that together you'll get an x to the power 4. The roots are also satisfied because if you plug in I minus I plus 2 minus 2, you'll find that the polynomial vanishes. And then p of 3 equal to 25, that's also something that you can check along the lines we did here. Now, for the second example, let's find a polynomial with roots -2 and 0 of degree 4 again. And now a special twist. We want the root with -2, we want that to have multiplicity 3. And so that's a concept that we haven't seen before. So what is the multiplicity of a root? So h has multiplicity p, where p is a natural number. If we can write the polynomial f of x as x minus h to the power p times another polynomial. So it's a root, h is a root, but you can take out this x minus h factor p times, so you get p here in the exponent. And so then for the problem that we're given, well, we want a polynomial f of x, and we want -2 to be a root. So we'll have a factor x plus 2, because the factor is always x minus the root. And now we say the multiplicity has to be 3, so we'll actually get 3 factors x plus 2, so x plus 2 to the power 3. And now 0 also has to be a root, so x minus 0 is also a factor, so we have to do times x. This is going to give me a degree 4 polynomial because I have an x cubed here times x, that's x to the power 4. But there are many such polynomials because I can still multiply this by an arbitrary constant, and not change the value of the roots. So in this case, this is the polynomial, or this is the family of polynomials that satisfies what I was asked to do. So here A is arbitrary.